Objective. The objective of this section is to explain A. Principle of isometric projection. B. Why it is required, its application. C. Problem-solving techniques. Contents. Objectives of this section: Axonometric projection, Introduction to isometric projection, Principle of isometric projection, Isometric scale, Isometric view, drawing, Methodology, Demonstration of practical application of the isometric concept, Problem-solving techniques. Axonometric projection. Axonometric projections are used to project an entire object in one image, unlike orthographic projections where the object is scattered among the top, front, and side views. Axonometric projection gives a three-dimensional picture in one view and is classified as a pictorial drawing. Axonometric projection classification. Axonometric projection is classified as a pictorial projection. A pictorial projection enhances one's ability to visualize an object as it gives a three-dimensional representation of an object. There are three main divisions of pictorial drawing. 1. Axonometric projection, with its division into trimetric, diametric, and isometric. 2. Oblique projection. 3. Perspective projection. Principles of projection. Principle of isometric projection. Isometric means equal measures. In isometric projection, an object is placed in such a way that its principal edges or axes make equal angles with the plane of projection. They are foreshortened equally. In the isometric position, the edges of a cube are projected equally and make equal angles with each other, 120 degrees. The isometric projection of a solid is represented on a vertical plane. In the given figure, a cube is placed in such a way that the principal edges OA, OB, and OC make equal angle with the plane of projection, and when they are projected on the vertical plane, they make equal angles of 120 degrees. Principles of isometric projection. Isometric position of object. When a cube is resting on one of its corners on the HP and its solid diagonal in the front view is perpendicular to the VP, then the front view of the cube represents the isometric projection. Step-by-step explanation. Consider a cube resting on the HP with two of its square faces making equal inclination with the VP. O', C' is the solid diagonal. Tilt the solid on one corner G' and make the solid diagonal parallel to HP. Draw the corresponding top view in this position. The solid diagonal OC in top view is parallel to VP. Rotate the solid diagonal OC in the top view perpendicular to the VP and then project the corresponding front view, which represents the isometric projection of the cube. The length of axis projection is equal to the length of the edges multiplied by 1.41 by 1.732 or by 0.816 approximately. Thus, the projected length is about 80% of the true length. Isometric projection. Isometric projection, step-by-step depiction. Isometric axis. Isometric axis. In the above slide, in the final isometric projection of the cube, OB, OD and OG make an angle 120 degrees with each other and are called the isometric axis. Any line parallel to one of these axes is called an isometric line, and a line that is not parallel to these axes is called a non-isometric line. Isometric and non-isometric lines. Isometric lines and non-isometric lines. A line parallel to one of these axes is called an isometric line, and a line that is not parallel to these axes is called a non-isometric line. In an isometric drawing, true length distances can only be measured along isometric lines, that is, lines that run parallel to any of the isometric axes. Non-isometric lines include inclined and oblique lines and cannot be measured directly. Instead, they must be created by locating two endpoints. Isometric and non-isometric planes. Isometric planes and non-isometric planes. The three faces of an isometric cube are isometric planes because they are parallel to the isometric surfaces formed by any two adjacent isometric axes. The planes that are not parallel to any isometric plane are called non-isometric planes. Isometric lines and planes. True length distances are shown along isometric lines. An isometric line is the line that runs parallel to any of the isometric axes. Position of isometric axis. Position of isometric axis. Isometric views can be arbitrarily positioned to create different views of an object. Selection of isometric axis. Views A is preferred as it reveals more detail about the object. Isometric view. Isometric view. The view drawn with true scale is called isometric view, while the view drawn with the use of an isometric scale is called the isometric projection. In isometric views, any rectangular solid resting on a face on ground, each horizontal face will have its sides parallel to the two sloping axes. Each vertical face will have its vertical sides parallel to vertical axis and other sides parallel to one of the sloping area. In other words, vertical edges are shown by vertical lines, while the horizontal edges are represented by lines making angle 30 degrees to horizontal, drawn by t-square and 30-60 degree square. Isometric projection versus isometric view. Isometric projection versus isometric view. Isometric projection foreshortened by 81%. Isometric drawing, no foreshortened, 100%. Important points. 1. All lines parallel to the isometric axis are isometric lines. 2. All isometric lines are foreshortened equally. 3. All other non-isometric lines may or may not be foreshortened. 4. The foreshortening ratio of such lines may vary disproportionately. 5. The projections of parallel lines are parallel. All measurements can only be marked on isometric lines. Method to draw isometric projection. isometric views. There are two basic methods for drawing the isometric views or projection: boxing method, coordinate method. Method to draw isometric projection or isometric views. Boxing method. Boxing method is used when many objects contain many non-isometric lines. The boxing in method for creating isometric drawings. The four basic steps for creating an isometric drawing are: 1. Determine the isometric viewpoint that clearly depicts the features of the object, and then draw the isometric axis, which will produce that viewpoint. 2. Construct isometric planes using the overall width W, height h, and depth d of the object, such that the object will be totally enclosed in a box. 3. Locate details on the isometric planes. 4. Darken all visible lines and eliminate hidden lines unless absolutely necessary to describe the object. Isometric drawing step by step. 1. Positioning object. 2. Select isometric axis. 3. Sketch enclosing view. 4. Add details. 5. Darken visible lines. Isometric drawing step by step. 1. Positioning object. 2. Select isometric axis. 3. Sketch enclosing view. 4. Add details. 5. Darken visible lines. In isometric sketch or drawing, hidden lines are omitted unless they are absolutely necessary to completely describe the object. Practical demonstration. To explain the projection of the axis, let's take a view of a cube so that its three principal faces are visible. Let's place a transparent sheet of perspex in front of the cube and draw lines where the front edges of the cube meet at a point. The angle between adjacent edges of a cube is always 90 degrees. After drawing the outline of the converging edges on the perspex, we can measure the angles between them. We can see that the angle between adjacent edges is greater than 90 degrees in all three cases. That is, mu greater than 90 degrees, beta greater than 90 degrees, and phi greater than 90 degrees. These are the angles between the projection of the axis. These axes are known as the axonometric axis. If the angle between all three axes are the same, then an isometric view results. Mu is equal to beta is equal to phi. If two of the angles are the same, then a diametric view results. Example, mu is greater than or less than beta. Beta is equal to phi. Finally, if all three angles are different, a trimetric view results. That is, mu is greater than or less than beta, which is greater than or less than phi. In third angle, the planes of projection are in front of the object, so the projection of the axonometric axis will be along the front corner of the object. The cube in the animation is in third angle, as the axonometric axis intersect at its front corner. These axes would be used to solve questions in third angle. However, in first angle projection, the planes of projection are behind the object, and so the axonometric axis will intersect at the furthest back corner. First angle projection is generally preferred to third angle projection in second level schools. Where the three edges of the cube meet at the furthest corner from the observer are the axonometric axes used in first angle. The axonometric axis, isometric axis in this case, for first angle projection are shown here using a hollow cube. Compare the axonometric axis of this cube with those of the cube above. In fact, the isometric axis can be placed in any desired position so that the object will be in the position that best describes it. However, the angle between the projection of axes must always be 120 degrees. If the object is considerably long, then it is customary to place the long axis horizontally for best effect. Here are some typical positions of the isometric axis. Foreshortening. The concept of foreshortening is a very important one in axonometric projection. Let us take two orthographic views. First angle, that is, elevation above, plan below, of a pencil, which is parallel to the ground, and take a view perpendicular to its length. Keep moving the pencil away from you until you are looking along the point of the pencil. A view along the point of the pencil, a point view, is a view parallel to the direction in which the pencil is pointing. The length of the pencil changed as you moved it from full length to a point view. Every time you moved the pencil away from you, its length appeared to get shorter, or it foreshortened. As the pencil rotates parallel to the horizontal plane, its elevation becomes foreshortened. The further you move the end of the pencil away from you, the greater the foreshortening. This is known as the degree of foreshortening. For example, if you moved the pencil from its starting position, full length, 5 degrees away from you, the 5 degrees is relative to the vertical plane, then the degree of foreshortening is very small, as the pencil appears only a little smaller than full size. However, if you moved it 85 degrees from its initial position, then it would appear very small, very near a point view. In this case, there is a large degree of foreshortening. Note, the pencil is initially parallel to both the vertical and horizontal planes. It is then rotated 5 degrees. The pencil is now no longer parallel to the vertical plane. The full 5-degree rotation can be seen in the plan view. When fully rotated, the pencil is perpendicular to the vertical plane and still parallel to the horizontal plane. Let us take the same cube as above to further illustrate this point. Starting with an elevation view of the cube, we see a square. The LOS in this view is perpendicular to the front edges, example AB and BC, and also to the back edges, example EF and HG. G is the lower corner, right behind C in the elevation. Because the LOS is perpendicular to these edges, they are true lengths. It is also important to note that in the elevation edges, AE, BF, CG, and DH all appear as point views. This is because we are looking parallel to these lines. Let us now rotate the cube about AD so that the elevation and end view are visible together. We are no longer looking perpendicular to the front face of the cube. What has happened to the edges AB and AE? The line AB has been rotated, just like the pencil above, so it appears shorter in this view, That is, AB has foreshortened. However, the line AE has gone from being a point view to a line view. This line still does not appear as a true length, so it is still foreshortened. How about the line AD? We are still looking perpendicular to this line, so it appears as a true length. Finally, let us rotate the cube vertically up about the line DG while holding point D on the ground. Now what has happened to line AD? Well, we are no longer looking perpendicular to it, so it now also has foreshortened. If you watch the animation, you will see the vertical height of line AD decrease. In fact, all the edges of the cube now appear foreshortened. If the angles between the projection of the axis are equal, that is 120 degrees, then all the edges foreshorten equally. This view is known as an isometric view. Also, when the angles between the projection of axes are equal, the axonometric axes are known as isometric axes. When the cube has been fully rotated, a point view of the body or long diagonal DG results, which only occurs in an isometric view of a cube. Numericals. 1. Problem. A hexagonal prism of base side 30 mm and height 65 mm has a square hole of side 20 mm at the center. The axis of the square and hexagon coincide. One of the faces of the square hole is parallel to a face of the hexagon. Draw the isometric view of the prism with hole to full scale. 2. Solution. Step 1. Draw the top and front views of the given prism. Step 2. Redraw the plane with the isometric axis and complete rectangular box. Step 3. Mark all the corner points of the solid as shown in the figure. Step 4. Join all the points in the top and bottom faces of the solid and complete the isometric view of the given solid. 2. Solution. Step 1. Draw the top and front views of the given prism. Step 2. Redraw the plane with the isometric axis and complete rectangular box. Step 3. Mark all the corner points of the solid as shown in the figure. Step 4. Join all the points in the top and bottom faces of the solid and complete the isometric view of the given solid. Numericals. A frustum of a square pyramid is of bottom edge 50 mm, top edge 25 mm, and height 50 mm. Draw the isometric view of the frustum in this portion. Solution. Draw the front and top view of the frustum of square pyramid. Redraw the plane in isometric axis with length, breadth of 50 mm and draw vertical with 50 mm height. Then complete the rectangle box. Mark all corner points. In the top base, the points T, U, V, W are marked with the help of lines LL1, NN1, MM1, OO1. Join all corner points of the frustum. Complete final view of frustum as shown in figure 17.313. Numericals. A cone of base diameter 40 mm and axis 60 mm is mounted centrally on the top of the square slab of side 60 mm and thickness 15 mm. Draw the isometric projection of the solids. Solution. Draw the projections of the given combination of solids, that is, cone centrally placed over a square prism. To draw the isometric projection of the square slab cone, draw the rectangle box with size of 48 mm into 48 mm into 12 mm. Mark the center point O1 of top base. Then draw the verticals with height of 48 mm. Mark the point O. Mark all corner points of square slab in the box. The bottom base of cone is drawn on the top base of the box by using the 4-center method. Join all corner points of the given solid. Then complete the final isometric projection. See the figure 17.393.